Hello students, good day and welcome to the third lecture in a series. So normally I always like to, whatever thing we do in engineering mathematics, I always like to explain to students the reason behind why we're learning a certain principle so that you understand how to use it in real life problems. You know, what is the essence of doing differentiation, integration, and all sort nots without knowing how to use it in real life problems? So the reason why we're learning Laplace transform is that, see, there are some engineering problems or real life problems. Most problems are in time domain, and solving problems in time domain can be difficult and cumbersome. So a man named Pierre Simon Laplace found a way to simplify this. He now proposed a theory whereby we can transform that. How can we transform from this time domain to another domain? He now proposed what we call a frequency domain, or called the S domain. So in this S domain, we can now have algebraic or differential equations that we can solve using known and simple techniques. You could even have simultaneous equation A and B that you can solve using your normal mathematical simple principles. So now let's define what the Laplace transform is. It's defined as, usually is a coily L of the function f of x. Now when you transfer it to the S domain, it now becomes a big F in the S domain S. So, and then the formula is given as integral from 0 to infinity e raised to power minus st f of t dx. Now this f of t is whatever you have that you want to transform. If you have g of t that you want to transform, g of t, this becomes g of t. So now let's take the first property. Let's assume that f of t equals to 1, constant function of time. That's the constant function of time. Now Laplace transform 1 will give us, so you multiply this by 1. You just change this, since we have 1 here, so it becomes 1 here. Now I said it in the previous talk. So let's assume s is always greater than 0, so we don't have an undefined number. So integrating this part, we have minus s, that's minus 1 over s. Integrating this guy, we have minus 1 over s, and we brought it out because it is a constant, e raised to power minus st, then 0 to infinity. And when you simplify this guy, remember your mathematics, your calculus, become 1 over s into, you have infinity, negative of a great infinity number. Infinity replaces t. So the negative of it tends to 0 minus 0 here becomes 1 plus 1. Get it? Plus 1. Sorry for my mouse. So when you integrate this, it becomes minus 1 times minus 1 over s and gives you 1 over s. So let's take another one to know, to understand better. Let's say Laplace transform e raised to power at. So you just substitute this guy in that, I said is the integral 0 to infinity e raised to power minus st dot e raised to power at was inside here. So, and this is e raised to power minus st plus at. Remember your indices, a minus s into t. So you bring a minus s. When you integrate this guy, a minus s is the constant, so it comes out, and then you integrate from 0 to infinity. So we integrate from 0 to infinity. If a minus s is greater than 0, that's the first condition. Look at it. You have a minus s here, Now a minus s is now greater than 0. That means that this value e raised to power a minus s of t will be a very big number, because you are not, this is not tending to infinity, so it will be a very big number, so it will be undefined. So that is why we wrote the Laplace transform does not apply, the limit diverges, so it's not ideal. So but if a minus s is less than 0, then that means that this will tend to 0, or s is greater than a. Is the same thing. When s is greater than a minus s become negative. So this is now defined, and then when you simplify that using the principle we used in the previous slide, you have this. So this is the value for the Laplace transform of e raised to power at. So we can check the continuity. Remember that the Laplace transform of 1 is 1 over s from the first slide, and it's the same thing as writing e raised to power 0t. Remember, this is a. This is a in our case. So you now have Laplace of a over t. So you have, and we've gotten for Laplace transform of e raised to power at as 1 over s minus a. So instead of, that means you can now put, if you put 0 here, since a is 0 here, it becomes 1 over s. So that we are just checking the continuity to show that it is continuous. So let's do for Laplace transform of sine at. So you put it the same in the formula, e raised to power minus st sine at dt. Let's call this guy y. But since there is t here and there is t here also, is dependent, so we cannot just integrate it easily. So we have to use what we call the integration by parts. So recall from integration by parts, where you have duv over dt equals to u prime v plus v prime v u v prime u v prime. So it's the inverse of the order. So you have this formula. So we use this now to integrate this by parts. So we make u prime equals to this, and then we now integrate, and it becomes u equals to minus, sorry, there's a mistake here, minus 1 over s e raised to power minus st, because when you integrate this, minus s comes outside and is 1 over minus 1 over s e raised to power minus st. Also you have v, then you now differentiate, v prime becomes a cos at. So you now put it in the formula in the beginning, integration by parts, that's uv, and then int minus integral value of u v prime. Please always cross check everything here. Try to work it on your own. So putting it there into this, substituting in this, you have this stuff. Then since s is a constant, this s is a constant, it comes out, and a is a constant, that's why you have a over s here, left with this. So but since we can't end here, because we have another dependent variable, that's t here, so we have to do another integration by parts. So we call this guy y, this is still our y. So we now make u prime e raised to power raised to power st, u becomes minus 1 over s e raised to power minus st, and v is cos at, v prime becomes minus a cos sine at, since it's the opposite now, so sine at. So y equals to, you put it in this formula again, in this formula. So y becomes this, and then we do an expansion. By the time we did an expansion, we brought out this guy. That's why it's painted in red. So this guy is now our former y. If you look at the first slide, the previous slide is now our y. So we can now replace this place by y. So from the previous slide, remember that y, this y, is equals to the integral value from 0 to infinity e raised to power minus st sine at dt. So this was already replaced it. So that's why we collected like terms from this right hand side to this left hand side. So these two like terms have been collected. So that's why you have it simplified here. Then we now integrate from 0 to infinity this guy here, this stuff. So that's when you integrate this from infinity, remember your sine 0 and your cos 0. Then you have it simplified to this. You have to do this step on your own. Just take a sheet of paper and try to look at how we arrive here. So you have 0 plus 1 into 0 plus a over s squared. So this now becomes this on this right hand side, and this guy remains. Remember, this guy is from here, understand? So you have this. So when you simplify this stuff here, you have y equals to a over s squared plus a squared. So you can also show that the Laplace transform of cos 80 equals to s over s squared plus a squared. These are well known derivations that we have in different maths textbooks. So I'm just trying to show you how those things were gotten. So let's go into, we are in the development now. So we are seeing how each of the Laplace transform is being developed. So let's go to linear operator and derivatives. Let's look for the Laplace transform of C1 f of t plus C2 g of t, where C1 and C2 are constants. So using our formula, we have integral from 0 to infinity e of st, and then this Laplace Laplace transform plus this guy, this Laplace transform, but all in brackets. So we're just replacing everything here. Since is what we want to get the Laplace transform, so we are just transferring it here, but we are multiplying by our factor e raised to power minus st. So this becomes, we can now expand this. So expanding this, we have this, each of them multiplied by e raised to power minus st. Then we can bring out the constants for each of the integrals. So you have C1 outside here, 0 to infinity e raised to power minus st f of t, and so on, and for this other guy also. So that means that, and this, remember, this is the same thing as the Laplace transform of f of t. So this is the Laplace transform of f of t. So that's why we just wrote it out there as the Laplace transform of f of t and Laplace transform of g of t for this guy. So we are now back to, so that means that when you have the Laplace transform of the sum of c1 f of t plus c2 g of t of different functions, you can have the it as the same as the Laplace transform of the summation of each of the functions. So let's find the Laplace transform of f of t. What is the Laplace transform of f of t? Let's see the solution. So it's the same thing as putting it in our formula, e raised to power minus st f of t. So recall, since it is dependent of t here, we have to use our integration by parts. So we make u equals to e minus st, u prime becomes minus s e raised to power minus st. We differentiate it, and then v prime is f of t. V equals f of t. We are now integrating and becomes this little guy. So therefore, putting it back into the equation, we have this. Collecting and then integrating, bringing s out here, and this is minus minus becomes positive here. So bringing this guy out, we have this, and then evaluating this from 0 to infinity, you have 0 minus f of 0 plus s l. Since this is f of t, the Laplace transform of f of t, so bringing it out, you now have L f of t equals to S L f of t minus f of 0. So this is a very useful notation we are going to use. So it is S L f of t minus f of 0. This 0 means that when the time is 0. So we can also show that when you have the second differential, that's f prime prime of t, that means you have differentiated twice, f of t. We can also show that it is SL f prime of t minus f prime of 0, because you already, then you can, which is now equal to s into, you already have the value of this one. So you have L, you now substitute there, minus f of 0. So it becomes s squared L f of t minus s f of 0 minus f of 0. So this turns derivatives to differential equations. So try to work out the Laplace transform of f triple prime of t. You find out that it will be something s cubed. You see how it is worked out in the other slides. Now, you remember we asked a question. Let's go back. Since we've learned some principles now, let's use it to solve for L cos AT. Now, recall this. LF of t is equals to SLF of t minus f of 0, which we have proved in the previous slide. And then we already know that L sine A of t equals to A over S squared plus A squared, which I've already proved also. Now let's assume that f of t is cos AT, and then f prime of t is cos AT, then f of t becomes 1 over A sine AT. Then we now substitute it into the equation. We have s into Laplace transform. Since we have f of t, we just put 1 over A sine AT minus 1 over A sine 0. Since we are now integrating at 0 here, so it becomes sine 0. So simplifying these terms and collecting like terms, we have SL 1 over A sine AT comes to this side is equals to SA dot A S squared plus A squared, and it becomes A cancels A. We have S over S squared plus A squared. So that's what we have proved now. So let's look at the Laplace development for polynomials. Let's recall that the Laplace transform of 1, there are curly brackets here, is equals to 1 over s, which I have proved in the previous slides. And the Laplace transform of f prime of t, that's the second differential, is equals to SL Laplace transform f of t minus f of 0. So the Laplace transform of f now is 1 over s. What I just did there was that I brought in like times. I brought this out. Laplace transform of f alone is now equal to 1 over s lf of t plus f of 0. So f of 0 comes to this guy here, and then you divide by f of s. So this is Laplace of f of t, sorry. So we are now finding Laplace transform of t. So that means we are replacing whatever we have by time t. So what we have now is Laplace transform of t now become 1 over s Laplace transform of 1. Why it's 1? Because f of t here is now replaced by t. So I mean we are differentiating this t. So differentiating t raised to power 1 gives you 1 with respect to t, gives you 1. So that's why Laplace transform of 1 plus at 0, at f of 0, it will give you 0. So it becomes 0 here. So that is equals to 1 over, and we know Laplace transform of 1 as 1 over s. So it becomes 1 over s times 1 over s. So that's why we have 1 over s squared. So also we can find Laplace transform of t raised to power 2. So it becomes Laplace transform of, differentiate this 2t, t raised to power 2. The differential value of 2 raised to power is 2t. So Laplace transform of 2t, and we know the Laplace and plus 0. So you know the Laplace transform of 2t as 1 over s squared. So you have 2 raised to power s cubed. And then you can also find Laplace transform of s t3. So it will be 3t squared, Laplace transform of 3t squared. And then you multiply recursively and you have 6 raised to power s4. Please practice this one. Go back, go to the notes and practice it on your own. So we now have a general formula. Since you have for L of t as 1 over s squared, you have this as 2 over s cubed. You can now see that there is a general formula, geometric progression, whereby you have n factorial, that is 6 for Laplace transform of t raised to power 3. When you substitute in this formula, you have 3 factorial, which is 6, all over s into, this one is increasing by 1, n plus 1, that's 4. So that is, you can have the Laplace transform of t raised to power n value. So this becomes the general formula for it. So let's go into the principle of shifting transforms. So we recall from the previous slide that the Laplace transform of f prime of t is SL f of t minus f of 0, and then the Laplace transform of L double prime of t is s squared LF of t minus SF of 0 minus f prime of 0. Now let's use these two principles to now get the same analogy for f triple prime of t, which was the question we asked in the previous slides. So this now becomes, look at how it is, s raised to power 3. Since we have 3 differentials, s raised to power 3, you start there. L, that is the Laplace transform of the function f. Whatever you have, if it is y, it will be y of the function, minus s, now minus 1 to f of 0, minus, this one reduces by 1 again, s, f, this one increases by differential, f prime of 0, then minus again, f, this one reduces by 1, so it cancels off, it becomes 1 here, f double prime of 0. So this is the Laplace transform of triple differentials. So for fourth, we can find it also easily. S raised to power 4 LF of f minus, this one reduces by 1, s raised to power 3 f of 0, this one reduces by 1 again, s squared f double prime, f single prime of 0, s triple double prime of 0 minus f triple prime of 0, f of 0, sorry. So from the first definition, we have that when we have the Laplace transform of y of t, you can write it as a function of, in the s domain, of big Y in the s domain. This big Y is different from the small y. This big Y is already the integral. We have added the integral. So we are just representing everything here by the big Y of s, a big Y function of s. Now, Laplace transform of a of t, f of t will now become Laplace transform, that's 0 to infinity es of t times ea of t, multiply by this. So you now have minus sa of t, which can be written as minus into minus s minus a f of t. Now look at it very well. You know you have e raised to power minus s before, s of t. E raised by, there's t here, sorry, t here, t here. E raised to power minus f of t, f of t. This is the function, a big function of s. Now look at this very well. Now instead of having minus s of t here, you are now having s minus a. So we can easily write that this is a function of s minus a. So note that in your memory. So remember that LF of t equals to f of s, which is this. It's just what I've written here. So f of s is this. So that means when you have anything here apart from minus s, it will be the function of that. In this case, we have s minus a. That's why it's a function of s minus a. So for example, let's look at this example now. This is very, very important. You have the Laplace transform of cos 2t. Remember from our definition, you have s into s squared plus a squared, is it not? And our a is 2 here, so we have a squared. That's why this is 4. So you have s over s squared plus 4. No problem about that. Now look at this other one again now. Here you have e raised to power 3t and you have cos 2t. Normally you are supposed to have s here, is it not? Now this is now a function, is not now a function of just s. It's now a function of e of s minus 3, because your a is now 3 here. Instead of 80, you have 80 here. So your a is now 3 here. So that's why this is a function of s minus 3. So anywhere you see s, you can replace it by s minus 3. So you have s minus 3 divided by s minus 3 all squared plus another double a, which is 2 here. You have 4. So these are the shifting theorems that we can use. We are going to apply it a lot. So you can go to the workbook and then look at how you can evaluate the Laplace transform of so many different kinds of functions, using just transferring to the Laplace transform using these principles. So in this course, we've taught ourselves basically all these things we have done. We've done a lot of provings and we have done a lot from the first principle so that you can understand better. So just go back to the video, listen to the video very well, and do some other research again. You can go to YouTube and type in development of Laplace transform and learn more if you don't understand this video, but I'm sure you will understand this video. Just take a pen and paper, make sure you are solving along the video, not just reading and listening to it. So we'll see next week. Next week we'll go deeper into the Laplace transform by looking at some variations of using the Laplace transform. We'll talk about the step function. Then before we go to the Z transforms and then the inverse transforms, then we'll now see how we can apply Laplace transform to differential equations. Thank you for listening. Have a wonderful week. So let's start with the step function. Now you notice that there are some engineering systems that do not present as continuous systems, that maybe their sine wave or whatever wave to define the model is not continuous, and it may be difficult to model those kind of discontinuous systems. So that's why we need to take cognizance of the step function. So there are some systems that could behave in maybe you have a part whereby you have no response, then you could have a response, then a waiting response for a long time, another path of no response, then a waiting response again, like that. So some systems could behave like this. So in this case, we can approximate their model to a step function whereby there will be a jump in the performance, of the system. So that's why we need to define a step function, and it's defined as u of c of t, where t is on the time zone to show the jump, the point at which there is a jump. So you have when t is less than c at all these points, your UC, your graph is 0. Then when t is greater or equals to c at this point, your graph now behaves with value of 1. So that's why you have this graph this way. So this is the definition of a step function. So let's see how we can model it using the Laplace transform. So now let's consider a shifting function. Most functions may not exactly present like the previous slide, but let's consider when you have a shifting function. I want to see how we can approximate a new function given an original function. That's what we are trying to do in this slide. So you have your c, where there is this jump. This is the function f of t, and then this is the function whereby there is a shift of minus c, where you have f of t minus c. You can see that these graphs behave almost exactly like this graph, or exactly like this graph. But in this graph, it starts from this origin here. This one starts from this origin, but this one is shifted with the value of c towards the right. Shifted with the value of c before it starts behaving. Now, using what we know in the previous slide, when u of c equals to 0, the function is 0. That is, there's no jump. But when u of c is equals to 1, it behaves as f of t of c. You can see from this equation here, when uc of t is 0, everything becomes 0. You have this point here. So this graph of ft of c is like this. You have this, then you have this jump here, like that. So when uc of t is 0 here, everything here, this point here becomes 0. But when this is now 1, then you now have ft of c. So everything behaves like ft of c. So since we already established this fact, whereby we have that this one is 1, so that we have everything behaving like ft of c, we can now find a Laplace transform of this guy. So when we find the Laplace transform of this guy, that means we have now found how to model ft minus c. So that is the idea. So when we have the Laplace transform of this, we'll have the behavior of that function. So now let's begin. From the definition of our Laplace transform that we did last week, when you have the Laplace transform of this is equal to, don't forget your e raised to power minus st and then the function, the t. Now, to solve this, let's x be t minus c. dx dt is equals to 1, because when you differentiate x here, you have this as a constant, so it's 0, so you have dx dt. So dx equals to dt. This is established. Now let's remember that at t equals to 0, the unit step function is 0. Therefore, we can replace t equals to 0 with t equals to c. So instead of integrating from 0 to infinity, because at 0 everything is 0, remember the graph. So let's integrate from c, since we only have values right from c. It's only from c we have the value. Remember the graph. At 0 there is no value. So now plugging in t equals to c and t equals to t equals to infinity, we have this. Now, which is this value. We're just repeating everything here. Now replace again with x, and note that when t equals to c, when t equals to c now, x equals to 0. So you now have what we have in the next slide. So that means we replace this with 0 now to infinity, and then replace everything with x. So you now have e of x, x plus c, fx dx, and then simplified, since this is a multiple of indices, you can bring them in this way, f of x dx. And then this is now a constant, since this integral is not dependent on x. This value e raised to power minus sc is not dependent on any value of x, so it can come out as a constant. So that's why it's a constant here, and then you have this that you can integrate from 0 to x. Now remember that this value, that's why I painted it yellow here, this value is our Laplace transform of f of x. You know, the Laplace transform of f of x is e raised to power minus x sx into f of x. Or you can say f of t. You can replace everything by t. So therefore, the Laplace transform of a step function is f e raised to power minus sc, which is the constant, multiplied by Laplace transform of f of t. So we can hold this one. You can keep this one in your memory. So let's take an example to see how we can apply that. So let's find an expression for the Laplace transform of this. L into u pi t sine t minus x minus pi. So let's recall what we've just done previously, that the Laplace transform of this is e raised to power minus sc multiplied by lf of t. So let's substitute. We have e raised to power minus pi s, because you are now substituting c. Your c is now pi. C pi x Laplace transform sine t. Because this is just showing that it's shifting by minus pi, it's shifting by pi, but the Laplace transform is the value of what is there, that is t, not the pi. So it is just the shifting value. So when you have t minus pi, what you are taking, it will be t, the unshifted value. We'll see many examples like that so you understand better. So remember that from what we have done last week, the Laplace transform of sine t is 1 over s squared plus 1. So therefore, you can now write that the Laplace transform of what we are looking for is e raised to power minus pi s, this is out, divided by this. So now let's go into inverse transforms. Inverse transforms, inverse transform is just what you are. Maybe you have a function, you already have the Laplace transform of a function, f of t. You have the Laplace transform of this function equals to maybe something big F of s. Please, you should be constant with this notation. When you have the Laplace transform of f of t, it becomes big F. This big F is just, you can write e raised to power minus s of x, f of t. So it can be replaced by big F of s, just a big function whereby we have omitted the e raised to power minus s of x. So f of x, so you can write it like this, just like this. But somebody who is a good mathematician will know that this is broken down. This big thing can be broken down. So, but for convenience sake, we can just write big F of s. So now the inverse of it is now going back from the result back to get what is inside this. So that's what we mean when we are doing inverse transforms. So we are going to do a series of that because we are going to use it in solving differential equations. So let us remember all the proofs that we have done last week. Laplace transform of 1 of t raised to power n sine at cos at and so on and so forth. And this one that we just got now, Laplace transform of this is what we have got here today. And this too, which is obvious. This is what I just wrote here. So it's the same thing. So example, find the inverse transform of f of s equals to 3 pi s minus 2 raised to power 4. Now from your table, the table should be in your head. You should memorize the table, what we have done, so that you'll be able to easily refer to them. So at first inspection, you may see that the Laplace transform of t raised to power 3 equals to this. But this does not look exactly like this, because this s is minus 2 here, raised to power 4. So that means that from our shifting theorem, the s has been shifted 2 places to the right. So that means that you have a shift towards the right. So 2 places before the function starts behaving. So that's the meaning of that, instead of at this point. So our problem is in the form of this. Since there is a shift, so it's in the form of f of s minus, is a function of s minus a plus this guy here. So therefore, the Laplace transform inverse, that's the inverse Laplace transform of what we are looking for, is equal to e raised to power 2t, because our a is 2, shifted 2 places, and then the function t raised to power 3. Please try to go to the textbook, and if you don't understand, by the time you do it several times, you will understand better. So you can go backwards to prove that at your own convenience. You can find the Laplace transform of that, and then try to go back to get this value. So let's take another example so that you can understand better. So you have f of s is this. We want to get the inverse Laplace transform. So in this, we will first of all try to look at it in a way whereby we have the denominator, we have the numerator. What about if you think of it, what about if we get the denominator? Most of the Laplace transform we have maybe s squared plus a squared. Then you have, for the sine, I think so, is a, and for the cos is s divided by s squared plus a squared. So what if we get the denominator in this form? That is the idea, to get the inverse Laplace transform. So all we are trying to do, first of all, is to try to look at the denominator and get something in this form. So factor out the denominator, and then when you factor out using the completing the squares, you get this value here when you factor it out. So look at it. It now looks something that is reasonable and compared to this. At least we have s squared plus a squared is now in form of s minus 1. That means that there is a shift by one term, right? So plus 1. This can act as a squared. So we are getting somewhere. So let's recall that Laplace transform of cos t equals to s over s squared plus 1 or a squared. That's a is 1, right? But not quite. There has been a shift in the s minus 1 term. That means that s minus 1 has shifted one term to the right. So then the Laplace transform of e raised to power 1t, this is representing at, cos t equals to s minus 1 all squared plus 1. If you do the Laplace transform of this, therefore f of s can now replace all this value here. That is s minus 1 squared plus 1. So taking this, I just substituted f of s as this, not this same f of s, please. So f of s, you can call it anything. You can call it k of s or whatever. So you recall that this is e raised to power minus s, that's this, the Laplace transform of this is equal to e raised to power minus s f big F of s. So that means you can now put f of s into this. So this one will now come out 2s minus 1 e raised to power minus 2s over times f of s. This guy, you see it in the next slide, but let me explain here. It will now be 2. This will be replaced by big F of s, then e raised to power minus 2s. So let's see what the next slide shows. You can see, you can rewrite it at this. So substituting back into what we are trying to do, you have 2 into this 2 is a common, is a factor. 2 into 2, u2, remember our c is 2, f t minus 2 shifted 2 times because of this minus 2 here. So you now have e raised to power f of t, but remember that f of t is e raised to power t cos t. Therefore, f of t minus 2 is e raised to power t minus 2 cos of t minus 2, the shifting theorem. Therefore, the Laplace transform, the inverse Laplace transform, what we are looking for is 2 into u2 t e raised to power t minus 2 cos t minus 2. So please try to work it on your own. I did not, as much as possible, I try not to skip some step, but try to understand. It's quite confusing, but by the time you do some examples, you understand better, especially when it shifts. The shifting theorem is quite confusing, I must tell you that, but when you try to work out many examples, you will understand when to shift, what to use as your a in some instance, what to use as your s in some instance. Please try to do many examples.